KBYP back in the saddle after a DX vacation, and on part 7 of dealing with the Eimac information, trying to make heads or tails out of it. If you've been following this information closely, you've gotten absolutely nowhere, just like I didn't. This information is obfuscatory at best. After some careful looking and careful thinking, it becomes obvious that something is missing here. We've got the plate curves, we've got the operating case data, we've got some assumptions or calculations. We don't have a circuit. So go back to the plate curves here and notice the curves, obviously, and the operating lines that I've plotted. One here, one down there, one down here. Just some what ifs. And notice this little comet streak across here. That little line going that way. It's a very, very important concept to note that lines go 2 different directions on this graph. What's missing is the circuit. And the circuit, from a reading of Radio Engineer's Handbook, especially the part about Class C amplifiers, understanding that this tube data also includes harmonic amplifier. And knowing this information is from quite a few decades ago. This is a circuit to which they allude, but they're too cheap and lazy to publish. Thanks, guys, for making our lives difficult. Tube on the left. Parallel resonant tuned circuit on the right with a parallel R sub L load resistor going to B+. This is the circuit in the Radio Engineer's Handbook by Terman on Class C amplifier. The tube data, the Eimac data, especially the calculator, allows calculating power output for fundamental second and third harmonics. But the harmonic power levels I calculated were something like 230 on the second and 30 on the third harmonic. They're way too high level for the normal amplifier working into a tuned network like a pi network. What that circuit is this, taking plate current through the inductor in a parallel resonant tank at the operating frequency, whatever it is, fundamental 2 or 3. When that parallel network is resonant, it essentially disappears and leaves a series fixed resistor. Well, obviously, in series with the tube. But notice the notation, variable. Notice the dashed line. That's representation of what the tube is doing. It's not obvious how we get there, but that's what it is. How we get there is going back to this set of graphs and those lines, and noting on the lines in mathematics, as we say, decreasing to the right. This line here is decreasing as X values, or in this case, plate voltage values, increase to the right. That's decreasing to the right. This line is increasing to the right. Notice that if we take values of plate voltage on the x-axis and these plate current values over here, and we calculate various points along this line, what we get are differing resistance values, and that is uber critical. That's kind of sort of ought to be obvious. I wanted to know where this plate resonant load resistance comes from, and a resistor can't be resonant. But where's that resistor at? Well, I plotted this line for 2750 ohms, which is the resonant plate resistance, or the resonant load resistance for the 2 kV minimum distortion case that I've been working with in these videos. That's that line. There's a super, uber, mega critical observation here that is hiding. Very well hidden. And that observation is that these lines and this circuit will not work for a power amplifier. Now, yes, that circuit will act as a power amplifier, but what I mean is the traditional circuit with the tube with a inductor and a plate, and instead of that output network, a pi or T or some kind of matching network across the tube. It is not obvious, A, that that's the case here, and B, why that's important. But this data cannot be used, can't be used whatsoever to analyze a real amplifier with a series inductance in the plate. The way to stumble onto this observation is to go to Terman, Terman, Radio Engineer's Handbook. It's a real book. For those of you that grew up in the internet age, books have paper. This is paper, see? We can write on it. Terman says, not about the amplifier, not about the tube, but in the case of the real amps that we're going to build, in the case of the output network, which is usually a pi network, it absolutely must have a fixed value of resistance on the input to the network and the output. And if it doesn't, it will not work. It is a fixed transform. A pi network is a transformer. And if you read earlier in Radio Engineer's Handbook on Transformer section, you'll find that. So, it is not possible to have a resistor in the plate and put a pi network across the tube to the output. It will fail. Now, this type of circuit here with resistance is what's used in Drake TR3 and 4. The resistor, for example, for the final driver is actually in series between the B plus notation and the tune tag. That harkens back to the so-called tune plate, tune grid era. But it's interesting to note that in that case, the output to the final amplifier, in the case of the final driver, its plate circuit goes to the grids of the final tubes. That output's taken across this network, not across the tube. And it's difficult to see from the schematics. But there's a critical distinction that this circuit with a resistor in the plate will not work if there's a pi network across the tube, because the tube resistance is variable. You need to look at these graphs and these lines very carefully and see this, because it's a critical concept that you can't use this for a real amplifier. This data and these lines are only for the cases that Eimacs gave under their test conditions with a resistive load in the plate. What they fail to tell us is it's in series between the B plus and the plate. All that gets thrown out when we go to a real amplifier with an inductance in the plate circuit. I'm going to be a meanie and not explain this any further. I could spend another 3 videos doing it. I've given you enough information to figure the rest out. But something really interesting happens when we analyze a real amp with an inductance in series with the plate. The plate curves are still valid because they represent the tube. We have to throw these lines out. I'll leave it to you to figure out how to do that, and you'll find this very interesting once you get the hint. But the hint is that circuit won't work with the plate to cathode working into a pi network out to a fixed resistance or a fixed resistive load. Will not work. So there's a challenge for you. Kate BYP's Figuring the Amplifier Out challenge. And I ate up a good bit of my vacation time figuring it out. And it's really an eye-opener when you get it. But unfortunately, Eimacs did not see fit to tell us that. But I guess their business was making tubes. They really weren't an amplifier manufacturing company. So I get it. But with all the time WHJI spent wasted publishing fairly trivial technical information, you would think someone who claimed to be an engineer could have stumbled across this and managed to produce at least one document explaining how to get to a real amplifier, and just instead of just giving a circuit with some typical values and making you guess at it from there. So if you follow these videos and you follow this one, you'll figure it out. Just do a little digging. KBYP.